Hi, my name is Romeo, and today we're talking about the human immunodeficiency virus, otherwise known as HIV. And I would like to remind you that I'm not a doctor, I'm not a physician, I'm not a medical student. I am just someone with access to the internet and have fact-checked everything that I'm presenting to you to my best knowledge. So with that being said, let's get into it. So while I'm mostly going to be focusing on how the virus affects the body, specifically in the circulatory system, I'm first going to talk about how the virus affects the body overall. And in order to understand HIV, you need to first understand that HIV is a virus, meaning that it doesn't behave like a bacteria. So, in that, we know that it's not a living thing, and we know that it needs a host cell in our body to reproduce in order to make new copies of itself. I am a white blood cell, more specifically, a CD4 plus or helper T cell, and that is HIV. Now, HIV is going to hijack me by going through the process of endocytosis to get into my cytoplasm. And that looks like a binding of its glycoprotein 120 to my receptor and co-receptors found on my plasma membrane. And when it gets into the cytoplasm, it unpacks everything it brought with it. And that is reverse transcriptase, integrase, and its own viral RNA. And it's going to use those things in order to make a copy of viral DNA that it can then integrate into the white blood cells, DNA, basically turning it into a factory for making HIV. And then once it does that, the viral DNA builds up inside the cytoplasm of that white blood cell. And when it gets to be too much, the viral DNA leave the white blood cell via exocytosis and rip apart the plasma membrane, which kills the white blood cell in the process. Now, an individual that this would be happening inside of, they would have no idea that this is even happening or that they're extremely highly contagious at this time because they would have no symptoms. The point that someone would even knows that they're sick at all with anything comes after the time that seroconversion has already happened. Seroconversion, in regards to HIV, is the time in your body that it realizes that there's something in there that it shouldn't have. And it responds with any one or any number of the symptoms below. Sometimes all of them, sometimes none of them. When it has none of them, it's called being asymptomatic. Someone who is asymptomatic during seroconversion is extremely highly contagious, but also showing no signs of being sick at all. The graph below illustrates the inverse relationship between CD4 plus cell count in blue and viral load count in red in patients who do not undergo treatment. So this is the basic shape that the life cycle of HIV would have if someone just refused medication. And at the very top, you see a bar that goes across it that has a yellow, a green, and a red section. The yellow section is all I've been talking about so far. This is where seroconversion happens. The tail end of this graph shows how exactly HIV kills. And that is by bringing the number of CD4 plus cells down to a level that opportunistic infections can invade the body. I just wanted to point out really quick how this graph is just a little bit misleading because it shows a hard line at 7 or 8 years where HIV turns into AIDS. And this is misleading because HIV does not turn into AIDS based off of years. It's the same virus, but the diagnosis for AIDS is only given when an individual has dropped below 200 copies of CD4 plus cells in their body. And with antiretroviral treatment, it's possible now that someone with an HIV diagnosis can live the rest of their life without ever getting an AIDS diagnosis. Brings me to my next point. Antiretroviral therapies have effectively made it so that the HIV diagnosis is no longer a death sentence, like it has been in the past. And that is because inside your body, it actually blocks the receptors that HIV needs to get into the white blood cell, effectively saving the CD4 plus cell and making it so that the virus can't reproduce. And this leads to what medical science defines as undetectable. This graph illustrates that same inverse relationship between CD4 plus cells and viral load count that we saw in the last graph. However, in this graph, the patient is on antiretroviral therapy. So after seroconversion, those numbers kind of just stay static and don't change. Everything that I have been talking about up until this point has been basically what people understand HIV to do. It lowers your immune system to a point where an opportunistic infection can come in and kill you that way. However, to say that this is the only way that HIV can kill is a little bit of a misconception because HIV can actually kill by itself. And it does this via inflammation, decreased platelet count, and decreased anticoagulants in your blood. And there's a lot of things that this deadly trifecta can lead to. So these three issues, inflammation, increased platelet activation, and decreased anticoagulants in your blood, lead to a multitude of different problems that can be lethal. And it only takes one of these events for someone to kick the bucket. On this slide, I've included 4 examples of ways that someone could die from those three issues, and they all happen to be my least favorite as well. Biotechnology and bioengineering are helping in the war against HIV in many different ways. One of those ways is with the creation of new drugs. One of those drugs is called leronlimab, and this is proving to be very significant because it is a subcutaneous injection that would be an alternative to taking a once-a-day pill, and it also is showing to have very low drug resistance as well as not really have a lot of side effects. And it's also showing to be useful in fighting cancer and fighting COVID as well. The other ways that biotechnology and bioengineering are helping in the war against HIV is with CRISPR-Cas9. CRISPR-Cas9 is essentially gene editing, and what they're finding they can do is actually delete the section of DNA that HIV places into the DNA of the white blood cell, and this would be an alternative treatment. Another way that biotechnology and bioengineering are helping is with the creation of a cure, and they are trying to isolate and integrate the gene from 5 people who have been fully cured of HIV, and their cases are a little bit interesting because they actually had like bone marrow cancer and HIV, and they tried a very experimental procedure for a bone marrow transplant using stem cells, and they found out after that that their HIV was in complete remission. So researchers are trying to reverse engineer that what happened right there to figure out what gene they have because they all hail from one specific region of Europe, and those people that region of Europe people from that region of Europe typically have a higher resistance to HIV. So they're thinking if they can isolate that gene and integrate that into someone's DNA, that would lead to helping find a cure. Another way that bioengineering and biotechnology are helping in the fight against HIV is with the integration of broadly neutralizing antibodies, and this would go on to be a vaccine. The image below illustrates how CRISPR-Cas9 can be used to block the receptor and co-receptors in a CD4 cell of a lab rodent. Science has helped us come a long way since the first person was infected in 1959. However, there's still a long way to go, and these are some goals that biotechnology and bioengineering have in sight for the war against HIV.